Rotation can dramatically stabilize a fluid motion. Many types of oscillations and wave motions occur in rotating flows, and there can be unexpected flow patterns. The large-scale motions of the atmosphere and the oceans, and even the motions of the stars and galaxies, are strongly influenced by rotation. We shall look at a number of experiments which show some of the effects of rotation. To keep things reasonably simple, we shall look mainly at flows that deviate only slightly from a rigid body rotation, and we shall confine our attention to homogeneous fluids. When we observe the motions relative to a coordinate frame rotating at a constant rate omega, the velocity vector u is measured with respect to the rotating axes. The inviscid fluid equation of motion then takes this form. This much of the equation is identical to the non-rotating case. The relative acceleration is balanced by the pressure gradient and the gradient of the gravitational potential. In the non-inertial rotating frame, two additional terms are present. They are acceleration terms, but they are customarily written on the right-hand side of the equation and interpreted as forces. One, the centrifugal force, depends only on relative position and can be combined with the gravitational potential. The other term is the Coriolis force, minus 2 omega cross u. The Coriolis force is directed to the right of the relative velocity vector u and is proportional to its magnitude. It is the Coriolis force that gives rotating flows their most peculiar properties. We'll use this turntable for many experiments. It's driven by a motor and variable speed transmission and is very accurately leveled. The circular cylinder inside contains water. The outer container is square and will reduce optical distortion when we fill it. We'll nearly always view the experiments from the rotating system, either in this camera mounted on the side or in this camera mounted on the top. First, we will use this vortex ring generator and launch a small colored fluid body horizontally across the cylinder. We are looking from above. The table is not rotating, and the marked fluid travels straight along the diameter. We start the turntable rotating counterclockwise as seen from above. After about 40 minutes, viscous forces have brought the water into a state of rigid body rotation. Again, we are looking through the overhead camera. There is no direct evidence that we, as observers, are rotating. To indicate rotation, we have placed the small arrow at the bottom of the frame. We'll use an arrow to indicate rotation throughout the film. Instead of traveling straight, the fluid body is deflected to the right, in the direction of the Coriolis force. The effects of Coriolis forces on an extended fluid region are substantially different. This is a result of pressure gradients induced by the motion itself. and happens in the reaction of the oceanic tides to the Earth's rotation. To illustrate this, we generate a surface gravity wave with a small disk that oscillates vertically. With no rotation, we adjust the disk frequency to produce the lowest resonant sloshing mode of the fluid layer. We sprinkle aluminum dust on the surface to mark the fluid motion. In this mode, particles on the surface move horizontally in a linear harmonic motion. Now let's repeat the experiment with the fluid in rigid body rotation. There is a resonant sloshing mode at a frequency 15% higher than before. However, the wave is no longer a standing wave, but a progressive one, in which a single crest travels clockwise around the rim. The fluid particles move together in clockwise circular paths. They deflect to the right in the same sense as the Coriolis force. Here now, at the same rotation speed, is a second resonant frequency, 13% lower than in the non-rotating case. This progressive wave moves in the opposite direction, counterclockwise. The particles again move in circles, but this time they are swerving to the left, contrary to what we would expect from the sense of the Coriolis force. This is a reminder that forces other than Coriolis forces are acting on elements of the fluid. In particular, the pressure gradient arising from the slope of the free surface has a different phase relation to the Coriolis force for this counterclockwise mode than for the clockwise mode. The main point here is that the interaction of fluid motions over the whole fluid region determines the local behavior. Two dimensionless parameters characterize the relative importance of fluid accelerations as against Coriolis forces. They are the Rossby number and the frequency ratio. These parameters arise naturally when one estimates orders of magnitude of the terms in the equation of relative motion. The required terms are of these orders. Sigma is a characteristic frequency, U is a characteristic fluid velocity, and L is a characteristic length. The Rossby number is U over L omega. It provides a rough estimate of the ratio of relative convective accelerations to the Coriolis force. The frequency ratio is sigma over omega. It estimates the ratio of local acceleration to Coriolis force. The vortex ring experiment was at large Rossby number. The sloshing experiments had high frequency ratios. In both cases, Coriolis effects were really rather slight. If the Rossby number is much less than 1, the relative convective acceleration is very small. And if the frequency ratio is low, the local acceleration is small. Under these conditions, there is a very close balance between the horizontal component of the pressure gradient and the horizontal component of the Coriolis force. A low Rossby number flow is called geostrophic, Such flows occur in the atmosphere and oceans, mainly because the scale of the motion is large. Now we'll do an experiment to demonstrate a low Rossby number flow. In this example, omega will be large and u small. This ping pong ball is filled with just enough water so that it is almost neutrally buoyant. It should therefore behave like a marked piece of fluid, for instance like the dyed vortex ring. It is tethered by a long fine thread to this line stretched around pulleys. A motor pulls the top of the thread straight across the diameter, but the ball is free to deflect sideways. We are looking from above. The fluid has been rotating 30 minutes and is in rigid body rotation. The Rossby number is low. The towing speed is really very low, but the action is speeded up by time-lapse photography. Except for a few wiggles, the ball goes straight across. In contrast, here is the high Rossby number situation. At low Rossby number, pressure reactions build up a horizontal pressure gradient, which exactly compensates the Coriolis force on the sphere, so that it moves straight across. The reasons are associated with the flow pattern around the sphere. Here we are looking from the side. Dye crystals leave traces which mark the fluid over the ball. When the ball is towed away, it does not leave all the dye behind as we might expect, but instead carries a column of fluid with it. The explanation lies in a theorem proved by Taylor and Proudman that depends on vorticity considerations. This theorem shows that for low Rossby number, low frequency ratio, homogeneous flows, the motion is nearly two-dimensional in planes perpendicular to the rotation axis. Fluid lines parallel to the rotation axis are also the vortex lines of the absolute motion and tend to remain parallel to that axis. Towing the sphere again, at low Rossby number and low frequency ratio, the two-dimensional Taylor column appears. We increase the towing speed. At this high Rossby number, the motion becomes three-dimensional and the Taylor column is left behind. Here's the same motion seen from above. When the ball is accelerated, it swerves to the right, like the earlier vortex ring. Now we have changed our setup so the sphere can be towed vertically, parallel to the rotation axis. The water is in rigid body rotation. Dye crystals mark the fluid above the sphere. We start towing at a very low Rossby number of about 1%. A few minutes later, we see that the dye is largely confined to Taylor columns above and below the sphere. We will speed it up by time-lapse photography. Above the sphere, the dye lines rotate clockwise. That is, there is negative relative vorticity above the sphere, where the vortex tubes are shortened. Below the sphere, the ink near the bottom shows counterclockwise rotation, where the vortex tubes are lengthened. These changes in spin are those implied by the Helmholtz vortex theorems, or alternatively, by the Kelvin circulation theorem. Pressure changes correspond to the changes in spin. There is an increase ahead and a decrease behind the sphere, so that the drag coefficient is very much increased. This has a strong effect on the terminal rise velocity of this slightly buoyant ping-pong ball. In a non-rotating fluid, it rises briskly, while in a rotating fluid, it rises much more slowly. Here it is again. I mentioned earlier that rotation can produce strong stabilizing effects. When neutrally buoyant ink is injected into stationary fluid, it spreads in a familiar turbulent way. When we inject the same amount of ink into this rapidly rotating cylinder, the initial vigorous three-dimensional motion rapidly declines in intensity as the marked fluid is squeezed parallel to the rotation axis. After a time, the motion has been converted to a strongly two-dimensional geostrophic flow in which the Rossby number and frequency ratio based on eddy size and velocity have become very small. The further decay of this geostrophic motion is much slower. Thus, while the system is highly stable toward the initial three-dimensional motions, damping them and converting their energy into that of other modes, it is nearly neutral to the two-dimensional ones. The dye is everywhere collected in Taylor walls, parallel to the rotation axis. The rotational stiffness of the axial fluid lines, or alternatively the resistance to changes of fluid circuit length in Kelvin's theorem, make possible whole classes of modes of oscillation that do not exist in non-rotating fluid bodies. Here we have a neutrally buoyant sphere free to move on a vertical thread. I give it an impulse and it oscillates in response to what is called an inertia oscillation in the fluid. We can study these inertia modes by exciting them with a small generating disk at the proper frequency. First, when the fluid is not rotating, oscillation of the plunger produces a disorganized flow of vortex rings shed from one side of the disk to the other. But with rotation and excitation at the proper resonant frequency ratio of 1 1/4, we produce an internal inertia wave mode with a nodal plane at mid-depth. Such oscillations with frequencies near the so-called inertia frequency 2 omega are common in the oceans and large lakes. Here is a top view of a larger body of rotating fluid, excited by a similar vertically oscillating disk. This mode is at a frequency ratio of 1/2. There are 10 or so rings of alternating, nearly zonal motions. Modes of this type with more rings have lower excitation frequencies. The reason is that the rotational stability acts mainly against radial displacements, and these become small relative to axial displacements as the rings decrease in width. We now increase the amplitude of oscillation. And you see the onset of one of the spontaneous instabilities for which Let's now look at a distinctly different class of oscillations known to meteorologists and oceanographers as Rossby waves. We have an inner cylinder and a conical ring at the bottom. The depth of the fluid in the ring between the two cylinders varies from about 3/4 of the mean depth on the inside to 1 1/4 on the outside of the ring. This variation means that in a low Rossby number motion, vortex tubes displaced radially must stretch or shorten and develop corresponding relative vorticities. The effects of the variation in depth are comparable to those of the variation of latitude on the spherical Earth. To produce the radial displacement of vortex tubes, we have placed on the cone a smooth radial mountain ridge whose height is only 1/40th of the mean depth. Notice the camera lens produces the perspective effect of looking down a long, shiny tube. This is the reflection of the mountain in the sidewall underwater. Outside this ring is a reflection of the top surface in the sides of the tank. The rotation has been going on for about 40 minutes. We generate a counterclockwise relative current by slowly reducing the rotation rate of the container. The speed of this current, about 4.5%, is such that a train of exactly 5 sinusoidal waves is excited downstream of the mountain. Now we repeat the sequence, this time with dye released at mid-depth. It forms a pentagon of exactly the same shape as previously seen at the top surface, thus verifying the two-dimensionality to be expected from the Taylor-Proudman theorem. So far, I have skirted the question of viscous effects. The Taylor-Proudman theorem, for example, does not hold in boundary layer regions for any Rossby number. Here, the tank and water were in rigid body rotation, and I have just increased the speed of the tank slightly. Dye tracers show that the main body of the fluid is rotating clockwise relative to the camera, while there is a strong outward flux in the viscous layer at the bottom. This is called an Ekman boundary layer. A vertical sinking motion in the fluid above is required to supply it. This flow in the inviscid region stretches the vortex tubes and increases their spin rate up to the new value much more rapidly than would otherwise be the case. The important feature here is that the primary motions in the inviscid regions adjust to and are affected more strongly by the matching requirements at the viscous layers than is the case in non-rotating flows with boundary layers. If the inviscid region currents vary from one place to another, the transverse Ekman layer fluxes vary, requiring exchanges of fluid between the viscous and the inviscid regions that may be quite localized. This cylinder has a central disc which is flush with the clear plastic bottom. The disc will be rotated at a slightly smaller speed than the cylinder. Ink has been injected through a central hole in the solid lid, which is in contact with the fluid. The interior fluid, out to the disc radius, adjusts to a rotation speed halfway between that of the disc and that of the upper lid. The accommodation to the no-slip boundary condition occurs in an Ekman layer on the disc and another Ekman layer under the lid. The fluid in the outside ring almost rotates with the cylinder. The ink has spread rapidly outward in the top Ekman layer to the same radius as the disc, and stops even though the lid is a single rigid sheet. It then descends in a thin cylindrical Taylor sheet with a hollow core, a so-called free shear layer, to the base disc edge. There it will flow inward in the disc Ekman layer, and eventually complete the circuit by a slow upward inviscid flow parallel to the axis. In this film, you have seen many of the effects that occur in nearly rigid rotations of homogeneous fluids. When Rossby numbers or frequency ratios are high, we often see rather direct reactions to the Coriolis forces. Or we may have distinct oscillations associated with the rotational stabilizing tendencies. When Rossby numbers are low, the strong vortex tube effects and geostrophic adjustment to the pressure field produce unexpectedly two-dimensional flow fields, low-frequency Rossby wave modes, and reactions to viscous forces that are quite unlike those of non-rotating fluids.